Hello viewers, my name is Adam Malachinski and I'm a first-year PhD student in Purdue's Earth, Atmospheric and Planetary Sciences Department working in the lab of Dr. Matt Huber. I'm currently focusing on climate modeling for our group's SharkFest research project. Our group's overall goal is to investigate the climate conditions in which the modern Antarctic ice sheet first formed during the transition from the Eocene epoch to the Oligocene epoch approximately 35 million years ago. Now you're likely thinking, wow Adam, that does sound interesting. What does it have to do with modern climate change? These videos are supposed to be about our current and future climate. And that's a good point, but I'd like to tell you that one of the biggest obstacles standing in the way of understanding our planet's natural climate responses comes from the gaps in our knowledge of climate sensitivity. We're still learning a lot about how the climate behaves in different conditions. Of course, carbon dioxide content in the atmosphere is going to have the greatest direct effect on surface temperatures, but we also need to understand the role of ocean currents, continental positions, biome types, and even the planet's position in its orbit. This is one of the goals of paleoclimatology. By understanding the hows and whys of the Earth's past climate, we can better understand how it will change in the future, which will help us become better prepared for what's to come. So with that out of the way, let me go into a bit more detail about my research. The Eocene-Oligocene transition, or EOT, is an interesting time for paleoclimatologists because the Eocene that preceded it was one of the warmest periods of time in all of the Cenozoic era. At its warmest, global average temperatures in the Eocene were in the ballpark of 23 degrees Celsius, and there were tropical plants and even crocodilians living in what is now the Arctic. So the mystery here is what caused the Earth to cool to the point of forming a permanent ice sheet during the span of the EOT. Our research group will be reconstructing ocean and climate conditions nearby the Antarctic coast, using the oxygen isotopes and neodymium ratios of fossil sand shark teeth recovered from the La Meseta Formation off of Seymour Island. This will give us one of the first high-resolution geochemical data sets of this location across EOT and will go a long way towards unraveling this mystery. My job, however, will not be directly involved in the collection of this data. Instead, I'll be using Purdue's own supercomputer resources to run paleoclimate models of likely scenarios that could have led to the conditions of EOT, including a sudden drop in atmospheric CO2, a shift in the ocean's deep water circulation regime, or even a combination of those two. I'll be using two models for this study. The widely utilized CESM 1.2 will be invoked for the final modeling results since it involves a variety of modeling components that are capable of simulating a very wide variety of oceanic and atmospheric conditions that might be important for ice sheet formation. However, since CESM can take a very long time to run, I'll be fine-tuning the scenarios with an intermediate complexity model called CGENI, coupled with the PLASM model for weather input. Running these simulations should give me a better idea of how to set up CESM before committing to a long experiment. When my model simulations are complete, the research team will compare the fossil sand shark teeth data to the experiment results and determine which simulation best matches their data. Model data comparisons like these are a common way to synthesize results in paleoclimate studies. And by better understanding the conditions in which Antarctic ice sheet first formed, we are gaining a stronger sense of the ice sheet's longevity and vulnerability to modern day climate change. Thank you for watching and have a great day.